Welcome back to Derivatives and Risk Education. In this video, we explore Markov processes, a class of stochastic models that simplify pricing, hedging, and dynamic programming in finance. Markov processes are memoryless. The future depends only on the present, not the past. This property makes them ideal for modeling asset prices, interest rates, and decision making under uncertainty. So what exactly is a Markov process? Let's define it precisely. A stochastic process, x0, x1 to xn, is Markov if this holds. So this means for every function f of the random variable x, at some point in the future n plus 1, there exists a function g, such that the conditional expectation depends only on the current state xn. We don't need to compute g explicitly. Its existence tells us that the current state summarizes all relevant information from the past. In our coin toss model, this means that the probability of heads or tails at future time n plus 1 depends only on the current node, not the path taken to reach it. Now let's compare the Markov property to the martingale property from the previous video, as they can seem quite similar. A martingale models fair value. The expected value at time n of the value of the random variable x at some time in the future n plus 1 is just the current value xn. A Markov process models memorylessness. The expected value at time n of any function f of the random variable x at some future time n plus 1 is equal to the expectation conditional on the value of xn. They are similar but conceptually different. A process can be both Markov and martingale, but not always. For example, the stock price in the binomial model is Markov under both the actual and risk-neutral measures, but it's typically not a martingale unless the expected return equals the risk-free rate. Let's look at an example which shows that the stock price is Markov. In the binomial model, the stock price evolves as follows. The stock price at time n plus 1 is equal to up factor u times Sn if the result of the coin toss is heads, or the down factor d times Sn if the toss is tails. Then, the expected value of some function f of the future stock price is the risk-neutral probability p times f of usn plus probability q times f of dsn. So this is our function g of Sn. So here the randomness enters through the next coin toss, but the conditional expectation depends only on the current price. So the stock price process is Markov. Multidimensional Markov processes. Sometimes one variable isn't enough. For example, consider the process Sn-Mn, where Sn is the stock price and Mn is the maximum stock price to date. Mn by itself forgets the current stock price. It just keeps the maximum. It can't determine alone how the maximum will evolve. But Sn contains all we need to know about the future evolution of the stock price, and when combined with M, the pair captures the full state needed for the next step. So the pair of Sn and Mn is Markov, even though Mn alone is not. So let's summarize. Markov processes are memoryless. The future depends only on the present. This simplifies pricing, hedging, and optimization. Many financial models, from binomial trees to Black Scholes, rely on Markov structure. When the payoff depends on multiple variables, we can often recover the Markov property by expanding the state. Thanks for watching, and don't forget to like, subscribe, and share with anyone learning quant finance.